Right now, at this very moment, something invisible is protecting you. It's not your roof, not your walls, not even the atmosphere you breathe. It's a force field. Yes, an actual force field, stretching thousands of kilometers into space, wrapping around our entire planet like a cosmic shield. Without it, you wouldn't be here. Nobody would. Life as we know it would have been impossible from the very beginning. This shield is Earth's magnetic field, and tonight we're going to explore what would happen if it suddenly disappeared. Not weakened, not fluctuated, completely gone. The consequences wouldn't just be catastrophic, they would be existential. Within hours, technology would begin to fail. Within days, the atmosphere would start to strip away. Within years, Earth could transform into something unrecognizable, a barren, radiation-scorched rock, more like Mars than the blue jewel we call home. But here's what makes this scenario truly unsettling. Earth's magnetic field has disappeared before, multiple times in fact, and it could happen again. The geological record shows us that our planet's magnetic poles flip every few 100,000 years, and during those transitions the field weakens dramatically, sometimes dropping to just 10% of its normal strength. We're talking about a real phenomenon, not science fiction. So what would those first moments look like? What would you see, feel, or experience? And more importantly, how long would we have? Before we dive deep into this journey through magnetic collapse and cosmic consequences, I need to ask you something. If you're finding this exploration fascinating, if you're curious about the invisible forces that keep us alive, please hit that like button and subscribe to the channel. It truly helps me continue creating these deep dives into science, and I'd absolutely love to know, where are you watching from right now? What time is it in your part of the world? Are you in North America watching late at night, Europe during your morning coffee, Asia in the middle of your afternoon, Australia winding down your evening? Drop a comment below and tell me. Let's build a community of curious minds together, spanning every corner of this protected planet we call home. Now, let's imagine the unimaginable. Let's turn off Earth's magnetic field and watch what happens, step by step, consequence by consequence, from the first second to the final transformation of our world. Take a deep breath. This is going to be quite a journey, and I promise you by the end of this video you'll never look at a simple compass the same way again. You'll never take the northern lights for granted, and you'll understand why we're so incredibly fortunate to live on a planet that still has this invisible shield, humming quietly, protectively, around us every single moment of every single day. Let's begin. To understand what we'd lose, we first need to understand what we have. And trust me, what we have is nothing short of extraordinary. It's one of the most remarkable features of our planet, yet most people go their entire lives without thinking about it even once. Earth's magnetic field, also called the magnetosphere, is generated deep within our planet's core, about 2,900 kilometers, roughly 1,800 miles, beneath your feet. Right now, as you're listening to this, below the soil you walk on, below the bedrock, below the tectonic plates, below the solid mantle, there's an ocean, not of water but of liquid iron and nickel. This molten metal ocean exists in a region of crushing pressure and extreme heat, with temperatures reaching 5,000 to 6,000 degrees Celsius, as hot as the surface of the sun itself. Think about that for a moment. Right beneath us, deeper than any human has ever gone, deeper than the deepest mine or the deepest drill hole, there's a sea of molten metal as hot as our star. And this metal is not sitting still, it's moving, churning, flowing in massive convection currents. This liquid metal is heated by two main sources. First, radioactive decay. Elements like uranium, thorium, and potassium, deep in Earth's core, are constantly breaking down, releasing energy in the form of heat. This has been happening since Earth formed 4.5 billion years ago, and it will continue for billions of years to come. Second, residual heat from Earth's formation itself. When our planet coalesced from the debris of the early solar system, the collisions and compression generated enormous amounts of heat. Much of that heat is still trapped deep inside, slowly radiating outward over geological time. The combination of this heat, Earth's rotation, and the Coriolis effect creates convection currents in the liquid outer core. Hotter, less dense metal rises toward the mantle boundary. As it rises, it cools slightly and becomes denser, then sinks back down. This rising and falling creates circular patterns, like boiling water in a pot, except this pot is thousands of kilometers across, and the liquid is molten iron, moving at speeds of several kilometers per year. This process is called the geodynamo. It's essentially a naturally occurring electrical generator, and it's been running continuously, without interruption, for billions of years. No maintenance, no fuel deliveries, no technicians monitoring gauges or flipping switches, just pure physics, operating flawlessly since before the first single-celled organisms appeared in Earth's ancient oceans. As the liquid iron moves through the outer core, it generates electric currents. This happens because the iron is electrically conductive, and when a conductor moves through a magnetic field, or when moving charges create their own magnetic fields, you get a self-sustaining loop. Those currents in turn produce magnetic fields, and those magnetic fields strengthen and organize the currents. It's a self-sustaining feedback loop, a cosmic engine that requires nothing from us, asks nothing of us, and yet protects everything we are and everything we've ever known. The result of this process, a magnetic field that extends from Earth's interior out into space, stretching approximately 60,000 kilometers, about 37,000 miles, on the side facing the Sun. That's more than 4 times the diameter of Earth itself. On the night side, away from the Sun, the field streams millions of kilometers into space, forming what scientists call the magnetotail. This tail extends so far that it occasionally reaches beyond the orbit of the Moon, which is roughly 384,000 kilometers away. Our lunar companion, in fact, passes through Earth's magnetotail once per month during its orbit, experiencing a brief moment of protection from the solar wind before emerging back into the harsh environment of interplanetary space. NASA's The MISS mission, Time History of Events and Macroscale Interactions During Substorms, mapped this structure in exquisite detail between 2007 and 2010. The mission consisted of 5 identical spacecraft positioned at different points in Earth's magnetosphere, allowing scientists to observe how the magnetic field responds to solar wind and how energy flows through the system. The data revealed something extraordinary. Our magnetic field isn't a simple smooth bubble. It's not like a soap bubble surrounding Earth. It's dynamic, constantly shifting, breathing, pulsing, responding to the solar wind like a living thing. It compresses on the sunward side where the solar wind pushes against it, sometimes compressing it to half its normal distance during strong solar storms. It stretches on the night side, creating that long tail that trails behind Earth as we orbit the Sun, like a comet's tail but made of magnetic field lines instead of dust and gas. The boundary between Earth's magnetic field and interplanetary space is called the magnetopause. It's not a hard barrier. There's no physical wall there, no surface you could touch. Instead, it's a region where the pressure from Earth's magnetic field exactly balances the pressure from the solar wind. This boundary is constantly moving, breathing in and out by thousands of kilometers, responding to changes in solar wind strength and direction. During quiet periods when the sun is calm, the magnetopause might be at its normal distance of about 60,000 kilometers. During a strong solar storm, it can be compressed to as close as 30,000 kilometers, bringing the edge of our protective bubble much closer to Earth's surface. Dr. James Green, former director of NASA's Planetary Science Division and one of the leading experts on planetary magnetospheres, once described it beautifully during a public lecture. The magnetosphere is Earth's first line of defense against the universe. Without it, we're naked to space weather. He paused for effect, letting that image sink in, and then he added something even more sobering. Look at Mars. Look at what happened there when it lost its magnetic field billions of years ago. That's our future if we ever lose this shield. Mars used to have a thick atmosphere, liquid water on its surface, possibly even life. Now it's a frozen desert with an atmosphere so thin you couldn't breathe it, even if it was pure oxygen. That phrase, naked to space weather, should genuinely give you chills. Because space weather isn't gentle rain and sunshine. It's not even terrestrial hurricanes and tornadoes, as violent as those can be. Space weather is radiation. It's high-energy particles traveling at a significant fraction of the speed of light. It's solar wind, a constant, relentless stream of charged particles, mostly electrons and protons, erupting from the sun's corona and spreading throughout the solar system. This solar wind would, without our magnetic shield, slam directly into Earth's atmosphere at speeds exceeding 400 kilometers per second. That's roughly 900,000 miles per hour. To put that in perspective, that's fast enough to circle Earth's equator in about 100 seconds. But right now, as you breathe, as you live your life, as you go about your day completely unaware, you're protected. The magnetic field deflects most of these particles, guiding them around our planet like water flowing around a smooth stone in a stream, and sending them harmlessly back into space. The magnetosphere acts like the bow of a ship cutting through water, creating a wake behind it. Except in this case, the ship is our entire planet, and the water is a hurricane of charged particles from the sun. Some particles do make it through, particularly near the poles where the magnetic field lines converge and dive down toward Earth's surface. The magnetic field is shaped roughly like a bar magnet, with field lines emerging from the south magnetic pole, arcing through space, and re-entering at the north magnetic pole. Near the poles, these field lines act like a funnel, guiding some solar wind particles down into the upper atmosphere. When they collide with oxygen and nitrogen molecules in the atmosphere, roughly 100 to 300 kilometers above the surface, they transfer energy to those molecules. The molecules become excited, their electrons jump to higher energy states, and when those electrons fall back down to their normal states, they release that energy as light. This is the mechanism behind one of nature's most spectacular displays, the aurora borealis in the northern hemisphere and aurora australis in the southern hemisphere. The northern and southern lights, those shimmering curtains of green, blue, pink, and red light, aren't just beautiful. They're not just Instagram-worthy photo opportunities. They're a visible reminder of the constant battle happening above us, invisible to our eyes except in these brief, colorful moments. Every photon of auroral light, every flicker and wave and curtain of color, represents a particle from space that our magnetic field captured, funneled toward the poles, and neutralized by having it collide with our atmosphere. It's a light show born from cosmic violence, transformed into something peaceful and mesmerizing. It's nature's way of showing us the shield in action, making the invisible visible for those lucky enough to live at high latitudes or to visit during the right season. The colors of the aurora tell us which gases are being hit and at what altitude. Green, the most common aurora color, comes from oxygen molecules at altitudes around 100 to 200 kilometers. Red, rarer, and usually only visible during strong auroral displays, comes from oxygen at higher altitudes above 200 kilometers where the air is thinner. Blue and purple come from nitrogen. The exact color depends on the type of gas molecule, its energy state, and the altitude at which the collision occurs. Scientists can study auroras to learn about the composition and temperature of the upper atmosphere, about the strength and direction of the magnetic field, about the intensity of solar storms. Auroras are not just beautiful, they're scientific instruments, natural laboratories displaying data in the sky. The European Space Agency's SWARM mission, a constellation of 3 satellites launched in November 2013, has been continuously measuring Earth's magnetic field with unprecedented precision. Each satellite orbits at a different altitude, 2 at about 450 kilometers and 1 at 530 kilometers, and together they create a 3-dimensional map of the magnetic field that updates constantly, showing us exactly how it changes over time, how it varies from place to place, how it responds to solar activity. Their data, collected over more than a decade now, has revealed something fascinating and, honestly, a bit concerning. The field is not constant. It's not a static, unchanging shield. It fluctuates hour by hour, day by day, year by year. It weakens in some regions and strengthens in others. The changes are usually small, a few nanoteslas here and there, barely noticeable in the overall field strength of about 30,000 to 60,000 nanoteslas depending on where you are on Earth's surface. But over years and decades, these small changes add up. The North Magnetic Pole, which compasses point toward and which is different from the geographic North Pole where all lines of longitude converge, is not fixed in place. It moves, and not just a little bit. Right now in 2025, it's drifting from the Canadian Arctic towards Siberia at about 55 kilometers per year. That's faster than a person can walk continuously in a straight line for a year. Think about that. The magnetic North Pole, which remained relatively stable in northern Canada throughout most of recorded history, has suddenly started racing across the Arctic Ocean toward Russia. This drift has been accelerating. In the 1800s, the North Magnetic Pole was moving at about 15 kilometers per year, a leisurely pace. In the 1990s, it had increased to about 15 to 20 kilometers per year, and now it's moving at 55 kilometers per year, more than 3 times faster than it was just a few decades ago. Scientists don't fully understand why it's accelerating. The most likely explanation involves changes in the flow patterns of liquid iron deep in the outer core, changes that affect where the magnetic field is strongest and where the field lines converge. But the core is so deep, so inaccessible, that we can only infer what's happening down there from measurements at the surface and mathematical models. And overall, when you average the field strength across the entire globe, the magnetic field has been weakening at a rate of about 5% per century for the past 150 years. That might not sound like much. 5% per century seems slow, almost negligible. but it means that Earth's magnetic field today is noticeably weaker than it was during the Victorian era, during the American Civil War, during Napoleon's time. Generation by generation, century by century, the shield is thinning. Over the South Atlantic, stretching from South America across to Southern Africa, there's a region called the South Atlantic Anomaly where the magnetic field is significantly weaker than anywhere else on Earth, about 30% weaker than expected for that latitude. This isn't a small area. It covers millions of square kilometers of ocean and land. Scientists believe this anomaly is caused by a peculiarity in Earth's core, possibly a region where the liquid iron is flowing in an unusual pattern, or where there's a patch of reversed magnetic field trying to emerge. Whatever the cause, the effect is clear. Satellites passing through this region experience higher rates of electronic errors and malfunctions because they're exposed to more radiation than usual. The Hubble Space Telescope, one of humanity's most valuable scientific instruments, automatically shuts down its most sensitive cameras and instruments when passing through the South Atlantic Anomaly to prevent damage from radiation.
The International Space Station's orbit, which is inclined at about 51.6 degrees and takes it over most of Earth's populated regions, occasionally passes through this anomaly. Astronauts have reported seeing random flashes of light, brief sparks in their vision even with their eyes closed, when passing through the region. These aren't external lights. They're cosmic rays, high-energy particles from space, hitting their optic nerves directly, penetrating the spacecraft's hull, penetrating the astronaut's skull, and creating false signals in the visual system. Imagine that. You're floating in the space station, eyes closed, trying to sleep, and suddenly you see flashes of light that aren't there. It's your brain interpreting radiation as visual input. That's happening right now, regularly, to astronauts aboard the ISS. And it's happening because the magnetic field in that region is weaker than it should be. This weakening is natural. It's part of a cycle that's happened many times before in Earth's history. We know from geological records, from studying the magnetic minerals in ancient rocks and seafloor sediments, that Earth's magnetic field has varied in strength over millions of years. Sometimes it's strong, sometimes it's weak, sometimes the poles flip entirely, with north becoming south and south becoming north. These geomagnetic reversals happen on average every 200,000 to 300,000 years, though the timing is irregular. Sometimes millions of years pass between reversals. Sometimes they happen relatively quickly, geologically speaking. But all of this raises an unsettling question, a question that keeps some geophysicists awake at night. What if the current weakening didn't stop? What if, instead of being part of a normal fluctuation that will eventually reverse and strengthen again, as it usually does, the field just kept fading and fading and fading until it reached zero? What if the geodynamo stopped entirely? What if Earth's magnetic field simply disappeared? Let's find out what would happen. Let's walk through this scenario step by step, hour by hour, day by day, year by year, and see how our world would transform. Imagine it's an ordinary Tuesday morning in March. Nothing special about the day. The calendar shows it's the 15th. You wake up to your alarm at 6:30 a.m., maybe hit snooze once or twice because you were up too late watching videos or reading. Eventually, you drag yourself out of bed, stumble to the bathroom, splash water on your face, You check your phone while the coffee brews, emails from work, news headlines about politics, sports, celebrity gossip, weather forecast showing partly cloudy, high of 18 degrees Celsius, 64 Fahrenheit. A normal day. Outside, the sun rises as it always does, painting the eastern sky in soft oranges and pinks. Birds sing outside your window, greeting the dawn. Somewhere down the street, you can hear the distant sound of traffic beginning to build as people head to work and school. A dog barks. A neighbor's car door slams. Life continues its familiar rhythm, the same rhythm that's been going on for your entire life, for generations before you, for millennia. But 2,900 kilometers beneath your feet, in the swirling ocean of molten iron that has churned continuously for billions of years since before the first bacteria appeared on Earth, something impossible has happened. The convection currents that have flowed without interruption for eons have stopped. The liquid iron, driven by heat from radioactive decay and Earth's rotation, has somehow, inexplicably, gone still. The geodynamo, that ancient, reliable engine that has generated Earth's magnetic field since our planet was young, has shut down. The magnetic field, which has protected life on Earth for billions of years, begins to collapse. Would you notice? Would anyone? At first, absolutely not. Not at all. The magnetic field is completely invisible to human senses. We can't see it with our eyes the way we can see light. We can't hear it with our ears the way we hear sound waves. We can't smell it, can't taste it, can't feel it on our skin, like we feel heat or cold or texture. It exists in a realm beyond human perception, detectable only by instruments, by compasses, by magnetometers, by specialized sensors designed specifically to measure something our evolution never prepared us to observe directly. Our ancestors had no need to sense magnetic fields. Knowing which direction was north could help with navigation, but that could be determined by observing the sun, the stars, the patterns of wind and waves. So we never evolved magnetic sense organs like some birds and fish and sea turtles have.
So when the field vanished, when it dropped from 30,000 nanoteslas to zero in a matter of hours, there would be no flash of light illuminating the sky, no sound like thunder rolling across the landscape, no rumble from deep underground like an earthquake, no physical sensation rippling through your body like a wave of pressure or heat or cold, just absence, a sudden silent void where protection used to be, the ultimate invisible catastrophe. But within minutes, literally just minutes after the field collapsed, instruments around the world would begin reporting anomalies, strange readings, impossible readings, compasses, simple magnetic compasses that have guided travelers for thousands of years by aligning their magnetized needles with Earth's magnetic field, would start behaving erratically. A hiker in Norway checking her compass to make sure she's heading north toward her campsite would watch in confusion as the needle spins wildly, pointing first toward a nearby iron deposit in the rocks to her east, then swinging toward a steel bridge half a kilometer to her west, then settling on some arbitrary direction, maybe northeast, maybe southeast, that has absolutely nothing to do with true north or magnetic north. She'd tap the compass, thinking maybe it's broken. She'd hold it level, making sure she's not tilting it, but the needle would keep wandering, searching for a magnetic field that no longer exists, because there would be no magnetic north anymore. Not anywhere on Earth, not in Norway, not in Canada, not in Antarctica. The concept of magnetic north would become meaningless. Ships at sea, from massive container ships crossing the Pacific to fishing boats off the coast of Iceland, would find their magnetic compasses suddenly useless. Modern commercial vessels rely primarily on GPS for navigation and on gyro compasses, which use a spinning gyroscope to find true north based on Earth's rotation rather than its magnetic field. So they'd maintain navigation. The captain might notice the magnetic compass spinning randomly and might report it as a malfunction, but the ship would continue safely to its destination. But older ships, fishing boats in remote areas, small craft in developing nations, vessels that still depend on magnetic compasses as their primary or backup navigation method, they'd be in trouble. Imagine you're a fisherman off the coast of Iceland, fog rolling in thick and gray, visibility dropping to less than 100 meters. Your GPS system malfunctioned yesterday, and you haven't had a chance to get it repaired. You're relying on your compass, the same compass your father used, the same type sailors have used for centuries, and suddenly it's spinning uselessly. You can't see the stars because of the fog. You can't see the coastline. You have no idea which direction is which. You're lost at sea with no way to navigate home. That's the situation thousands of vessels would find themselves in within the first hour. At research stations monitoring Earth's magnetic field, facilities scattered around the world like the Magnetic Observatory in Hermanus, South Africa, a beautiful coastal town where scientists have been measuring the magnetic field since 1932. The British Geological Survey's Escalamuir Observatory in Scotland, surrounded by quiet hills and forests, the Geomagnetic Observatory in Nîmes, Germany, which has been operating since 1890, scientists would see something unprecedented on their computer screens, something that should be impossible. The continuous magnetic field readings, displayed as graphs showing field strength over time, normally show gentle fluctuations around stable values, small variations from day to night as the ionosphere changes, larger variations during solar storms when the magnetosphere is compressed and disturbed, but always fluctuations around a mean value measured in tens of thousands of nanotelos. A typical reading at mid-latitudes might be 40,000 to 50,000 nanotelos, at the poles closer to 60,000, at the equator, lower, around 30,000.
But now, on this Tuesday morning, the graphs would show the field strength dropping rapidly, not fluctuating, not varying up and down, just dropping, falling, plummeting toward zero like a stone dropped from a cliff. 40,000 nanoteslas, 30,000, 20,000, 10,000, 5,000, 1,000, 500, 100, 50, 10, 0. The graphs would flatline, like a heart monitor when a patient dies, a straight horizontal line where there should be gentle waves. Dr. Kieran Beggan, a geophysicist at the British Geological Survey in Edinburgh, would probably be one of the first to notice. He monitors the magnetic observatories as part of his research on geomagnetic variations in space weather. His phone would start buzzing with alerts from the automated monitoring systems, messages from colleagues, urgent emails, all reporting the same impossible thing: the magnetic field strength dropping to zero. At first, he'd think it was an equipment malfunction, some kind of technical error, maybe a software bug corrupting the data. He'd check the backup systems. He'd call the observatories to ask them to manually check their instruments. But the reports would keep coming in from Scotland, from South Africa, from Germany, from Japan, from Australia, from Canada, from Brazil, from all over the world. Independent observatories using different instruments, different technologies, different calibration methods, all reporting the same thing: the magnetic field is gone. Within the first hour, emergency meetings would begin. Phone calls between scientists trying to confirm what they're seeing. Video conferences hastily arranged. Government agencies would be notified. NASA, the space agency that monitors space weather and geomagnetic conditions. ESA, the European Space Agency. NOAA, the National Oceanic and Atmospheric Administration in the United States, which operates the Space Weather Prediction Center. The Japan Aerospace Exploration Agency, Roscosmos in Russia. Space agencies and geological surveys from dozens of nations would scramble to verify the data, to understand what's happening. Is this real? Is it a measurement error? Is it global or localized? Is it temporary or permanent? Scientists would be pulling up historical data, checking whether anything like this has ever been recorded before. They'd be running through explanations. Could a massive solar storm have disrupted all the magnetometers simultaneously? No, that doesn't make sense. The magnetometers are designed to measure fields even during the most intense solar activity. Could it be a coordinated instrument failure? Extremely unlikely. These are independent systems maintained by different organizations in different countries. The only explanation that fits all the data is the one that seems impossible. The geodynamo has stopped and the magnetic field has collapsed. And while those questions were being asked, while scientists tried to wrap their minds around this catastrophe, while government officials began to understand the implications, the consequences would already be unfolding around the planet, silently, invisibly, but with terrifying speed. The first effects would occur at the edge of space, in the region where Earth's atmosphere gradually fades into the vacuum of interplanetary space, roughly 60,000 kilometers above the surface on the sunward side, the side facing the sun. Under normal circumstances, when the magnetic field is functioning, this is where the magnetopause is located, the boundary where the pressure from Earth's magnetic field exactly balances the pressure from the solar wind. It's a dynamic boundary, constantly shifting, constantly responding to changes in solar activity, but it's always there, always protecting us, always deflecting the solar wind around Earth like the bow wave from a ship. The magnetosphere, Our magnetic shield acts like an aerodynamic barrier in space. It's not a physical barrier, nothing solid, but it creates a pressure that the solar wind has to flow around. The solar wind, composed primarily of electrons and protons streaming outward from the sun's corona at speeds typically between 400 and 800 kilometers per second, sometimes faster during high-speed streams, carries its own magnetic field called the Interplanetary Magnetic Field, or IMF. When the IMF embedded in the solar wind encounters Earth's magnetosphere, the two magnetic fields interact. They press against each other like two magnets brought close together. The exact interaction depends on the orientation of the IMF. If it's aligned with Earth's field, pointing the same direction, they tend to slip past each other. If it's opposite, anti-parallel, pointing the opposite direction, then magnetic reconnection can occur, a process where field lines break and reconnect in new configurations, allowing energy and particles to transfer from the solar wind into Earth's magnetosphere. This is what causes geomagnetic storms and enhanced aurora displays. But most of the time, the magnetosphere just acts as a shield. The solar wind flows around Earth, diverted by the magnetosphere's pressure, like water flowing around a smooth stone in a stream. The pressure balance at the magnetopause holds steady, keeping the worst of the solar wind at bay, allowing only a controlled amount of particles to enter near the poles where they create the auroras. Now, remove the stone. Remove the magnetic pressure. Remove the shield entirely. Without Earth's magnetic field, there's nothing to create that pressure balance, nothing to deflect the solar wind, nothing to hold it at bay. The magnetopause, which had existed for billions of years, would simply cease to exist. The boundary would disappear. The solar wind, traveling at 400 kilometers per second or more and carrying an energy density of about 1 nanojoule per cubic meter, about 10 to the negative 9th joules per cubic meter, would slam directly into Earth's upper atmosphere with no barrier to slow it down, no shield to deflect it. This is not a gentle collision. It's not like a breeze blowing on your face. It's a cosmic sandblasting, an unrelenting bombardment of charged particles moving at a significant fraction of the speed of light, carrying kinetic energy that would begin stripping away our atmosphere particle by particle. The solar wind particles, primarily protons, which are just hydrogen nuclei stripped of their electrons, and electrons, each carrying kinetic energy from the sun's intense heat, would penetrate deep into the atmosphere. Under normal conditions, they'd be deflected away, sent streaming past Earth into the solar system beyond. But now, with no magnetic field, they'd hit the atmosphere directly. They'd penetrate particularly deeply in the regions around the poles, the Arctic and Antarctic, where Earth's atmosphere is thinnest. The atmosphere isn't uniform in thickness. It's thicker at the equator, where it extends higher above sea level because of the bulge created by Earth's rotation and because warm air rises more effectively. It's thinner at the poles, where cold air is denser and settles lower. This means the poles are more vulnerable to radiation from space, even under normal conditions. It's why polar routes for commercial flights receive more radiation exposure. It's why the auroras appear near the poles rather than at the equator. At altitudes of 100 to 500 kilometers, in the regions scientists call the thermosphere and exosphere, where the atmosphere is already so thin that individual molecules might travel kilometers before colliding with another molecule. These high-energy solar wind particles would begin slamming into atmospheric molecules. Nitrogen molecules, which make up about 78% of Earth's atmosphere. Oxygen molecules, about 21%. Argon, about 1%. And trace amounts of carbon dioxide, neon, helium, and other gases. Each collision would be violent on a molecular scale. A proton traveling at 400 kilometers per second has enormous kinetic energy relative to an atmospheric molecule that's essentially sitting still or moving slowly due to thermal motion. When they collide, that energy transfers. The atmospheric molecule absorbs the energy, and several things can happen. First, it heats up. The molecule's atoms vibrate more intensely. The molecule moves faster. This is how the upper atmosphere would begin to heat rapidly, absorbing energy from the solar wind bombardment.
Second, the molecule's electrons can jump to higher energy states. An electron orbiting an atom normally sits in its ground state, the lowest energy configuration. When it absorbs energy, it can jump to an excited state, a higher energy orbit. This is an unstable condition. The electron wants to return to the ground state. When it does, it releases that extra energy as a photon, a particle of light. The wavelength and color of that light depend on the energy difference between the excited state and the ground state. This is the mechanism behind auroras. When solar wind particles collide with oxygen molecules at altitudes around 100 to 200 kilometers, they excite the electrons. When those electrons fall back down, they emit green light at a wavelength of about 557.7 nanometers. That's the most common aurora color, the vibrant green curtains that appear in the night sky at high latitudes. Red auroras, rarer and usually only visible during strong displays, come from oxygen at higher altitudes above 200 kilometers, where the air is so thin that oxygen atoms can stay in excited states for longer before releasing their energy. Blue and purple auroras come from nitrogen molecules emitting light at different wavelengths. But here's what would be different if the magnetic field disappeared. Without the magnetic field to funnel and control where solar wind particles enter the atmosphere, limiting them to the polar regions, auroras would no longer be confined to high latitudes. They wouldn't just appear in Alaska, northern Canada, Scandinavia, Iceland, Siberia in the north, or Antarctica, southern Chile, Tasmania, New Zealand in the south. They would appear globally, everywhere, at all latitudes, low latitudes, mid-latitudes, equatorial regions. At all times of day and night. Imagine standing in the middle of a city far from the poles, New York City, at about 40 degrees north latitude, London at 51 degrees north, Tokyo at 35 degrees north, Cairo at 30 degrees north, Mumbai at 19 degrees north, São Paulo at 23 degrees south. Places where auroras never appear under normal conditions, where you'd have to travel thousands of kilometers north or south to see the northern or southern lights. Now imagine seeing shimmering curtains of green, red, and blue light filling the entire sky from horizon to horizon 24 hours a day. Not just at night when the stars are visible, but during the day too, faint but visible against the blue sky, shimmering and waving like ribbons in the wind. The sky would glow continuously as solar wind particles poured into the atmosphere from every direction, not just near the poles, colliding with air molecules at every altitude, creating a perpetual light show that would be both beautiful and terrifying. Beautiful because the colors would be stunning. The greens and reds and blues dancing across the sky, patterns shifting and changing, curtains appearing and disappearing, rays shooting upward like searchlights. People would stop on sidewalks, staring upward. Children would point and ask their parents what's happening. Cameras would capture images unlike anything in human history. Auroras over the pyramids in Egypt, over the Amazon rainforest, over the Great Barrier Reef. But terrifying because anyone who understood what auroras represent, anyone who knew the science, would realize those lights aren't just a spectacle, they're a visible sign of atmospheric destruction happening in real time, right above your head. Every photon of auroral light represents energy being deposited in the atmosphere, energy that's heating the upper atmosphere, exciting molecules, breaking chemical bonds. And more importantly, each collision between a solar wind particle and an atmospheric molecule has a chance of imparting enough energy to knock that atmospheric molecule free from Earth's gravitational pull entirely. This process is called atmospheric sputtering. It's like playing pool. When the cue ball moving fast hits the racked balls at the start of the game, energy transfers. Some balls roll slowly, some move faster, and if you hit hard enough at the right angle, some balls fly off the table entirely. The same principle applies here. High-energy solar wind particles are the cue balls, atmospheric molecules are the racked balls. Most collisions just heat the molecules or excite their electrons, but some collisions, the ones where the geometry is just right and the energy transfer is efficient, impart enough velocity to the atmospheric molecule that it reaches escape velocity, the speed needed to overcome Earth's gravity and fly off into space. Earth's escape velocity at the surface is about 11.2 kilometers per second, about 40,000 kilometers per hour, or 25,000 miles per hour. But at altitudes of 200 or 300 kilometers, where the atmosphere is thin and gravity is slightly weaker, escape velocity is a bit lower, maybe 10.8 kilometers per second. When a nitrogen or oxygen molecule gets hit just right by a solar wind proton and gains enough velocity to exceed escape velocity, it's gone. It flies upward, away from Earth, out into space, never to return. It becomes part of the solar wind itself, just another particle drifting through the solar system, one by one, collision by collision, molecule by molecule, atom by atom. The atmosphere would be eroding, being sandblasted away by the relentless solar wind bombardment. But this wouldn't happen overnight. It's critically important to understand this. Atmospheric loss is a slow process, even under the relentless assault of the unimpeded solar wind. It's not like someone opened a valve and the air is rushing out. It's a gradual erosion, a wearing away that takes place over immense timescales. NASA's studies of Mars, using data from the MEVN spacecraft, Mars atmosphere and volatile evolution, which has been orbiting Mars since 2014, specifically to study how Mars lost its atmosphere after its magnetic field disappeared roughly 4 billion years ago, estimate that Mars has been losing atmosphere continuously since then. The current loss rate is about 100 grams per second averaged globally. That sounds like a lot, but Mars has been losing atmosphere at roughly that rate for billions of years, and it still has some atmosphere left, thin as it is. For Earth, which is larger than Mars with stronger gravity and a much thicker atmosphere to begin with, the loss rate without a magnetic field would be higher, because the solar wind would have more particles to hit and more collisions would occur. But it would still be a relatively slow process measured in kilograms per second, not megatons. Let's use a reasonable estimate based on scaling up from Mars. Earth might lose somewhere between 100 grams and 1 kilogram per second. Let's take a middle value of 500 grams per second, about 1 pound per second if you're more comfortable with imperial units. 500 grams per second. That's about the weight of a can of soup. Lost every second. Doesn't sound like much, does it? But let's do the math and see how this adds up. 500 grams per second equals 30 kilograms per minute. That's 66 pounds per minute. 1800 kilograms per hour. About 2 tons per hour, using metric tons. 43,000 kilograms per day. 43 metric tons per day, or about 47 short tons if you're in the United States. In 1 week, Earth would lose roughly 300 metric tons of atmosphere, 300,000 kilograms floating off into space, gone forever. Now let's put that in perspective. How much atmosphere does Earth have in total? Earth's atmosphere has a total mass of approximately 5 times 10 to the 18th kilograms. That's 5 quintillion kilograms, or 5 million trillion kilograms, or 5 billion kilograms. It's an almost incomprehensibly large number. If you started counting 1 kilogram per second, it would take you 160 billion years to count to 5 quintillion, which is more than 10 times the age of the universe. So losing 300 metric tons, 300,000 kilograms in 1 week compared to 5 quintillion kilograms total is negligible. It's a tiny, tiny fraction. Let's calculate exactly how tiny. 300,000 divided by 5 times 10 to the 18th equals 6 times 10 to the negative 14. That's 0.000000000000000000006. 6/100ths of 1 trillionth. Less than 1 part in 10 trillion. You wouldn't notice it, not at all. Atmospheric pressure at sea level would still be about 101.3 kilopascals or 14.7 pounds per square inch, or 1013 millibars, or 760 millimeters of mercury, however you prefer to measure it. The air would still feel exactly the same when you breathed. There'd be no change in how far you could see, no change in the color of the sky, no change in how sound travels or how wind feels. In fact, even after a full year of losing 500 grams per second, Earth would have lost about 15.8 million metric tons of atmosphere. That sounds like a lot. 15.8 million tons. But compared to 5 quintillion kilograms, it's still only about 3 parts in a trillion, completely unnoticeable to human senses or even to most scientific instruments. But the trend would be undeniable to scientists studying the data. They'd see the measurements. They'd know that every single second, atmospheric molecules are being knocked into space, and they're not coming back. And unlike the immediate, potentially fixable damage to infrastructure that we'll discuss in a moment, atmospheric loss is irreversible on human timescales. There's no way to replace it. We can't manufacture atmosphere. We can't import it from somewhere else. Every atom of nitrogen, every molecule of oxygen, every atom of argon that gets blown into space by the solar wind is gone permanently. It's not coming back. Not in 100 years. Not in 10,000 years. Not in 1,000,000 years. Scientists monitoring atmospheric composition using satellite instruments, assuming any satellites are still functioning after the first solar storm, which we'll discuss shortly, would see the data and they'd run the projections forward. They'd calculate how long it would take at current loss rates to lose 1% of the atmosphere, 10%, 50%, and they'd realize the grim truth. Earth is on a one-way trajectory toward becoming a second Mars, a slow death, playing out over geological timescales, but inevitable, unless something changes, unless the magnetic field somehow restarts, or unless humanity develops technology to replace it. The models would predict that if the loss continued at 500 grams per second, measurable changes in atmospheric pressure, perhaps a 1% drop, would occur within about 10,000 years. That might sound like a long time, and it is from a human perspective. 10,000 years ago, humans were just beginning to develop agriculture. Writing hadn't been invented. The pyramids of Egypt wouldn't be built for another 5,000 years. But from a geological perspective, from the perspective of Earth's 4.5 billion year history, 10,000 years is the blink of an eye. It's nothing, and losing 1% of the atmosphere in 10,000 years, while not immediately catastrophic, would be just the beginning. Significant changes, a 10 to 20% pressure loss, would occur within 100,000 years. The atmosphere would become noticeably thinner. Breathing at sea level would feel like breathing at high altitude. Weather patterns would change. The climate would shift. Within a few million years, much of the atmosphere could be gone. Earth would have an atmospheric pressure similar to Mars, less than 1% of current levels. Liquid water could no longer exist on the surface. The oceans would freeze and sublimate, the ice turning directly to vapor, which would then be lost to space. The planet would become a frozen desert. But long before any of that happened, long before atmospheric pressure dropped enough to make breathing difficult or to affect the climate in obvious ways, other effects of losing the magnetic field would have made Earth increasingly hostile to life. Because while atmospheric loss is a slow long-term consequence, there are immediate and devastating short-term consequences that would begin within hours and days. And the first of those consequences involves something critical to life on Earth, something we rarely think about because it's invisible, and because it's always been there protecting us: the ozone layer. Let's talk about ozone. Not the ozone in smog, the kind that forms at ground level from pollution and causes respiratory problems. That's bad ozone, ozone where it shouldn't be. We're talking about the ozone layer. The good ozone, the ozone in the stratosphere, roughly 15 to 35 kilometers above the surface, that protects all life on Earth from the sun's ultraviolet radiation. Ozone is a molecule consisting of 3 oxygen atoms bonded together, written chemically as O3. Regular oxygen, the kind we breathe, is O2, 2 oxygen atoms bonded together. Ozone is less stable than regular oxygen. The 3-atom configuration wants to break apart, but in the stratosphere, there's a constant cycle of ozone being created and destroyed that maintains a relatively stable concentration. Here's how it normally works. High up in the stratosphere, ultraviolet light from the sun, specifically the highest energy UV called UVC with wavelengths shorter than 280 nanometers, strikes oxygen molecules, O2. The energy from the UV light is enough to break the chemical bond holding the two oxygen atoms together. The molecule splits into two separate oxygen atoms, just O. These free oxygen atoms are highly reactive. They don't want to be alone. They immediately start looking for something to bond with. When a free oxygen atom collides with an oxygen molecule, O2, they can combine to form ozone, O3. So UV light breaks O2 into two O atoms, and then O atoms combine with O2 to form O3. That's the creation half of the cycle. The destruction half happens when ozone absorbs UV light. Ozone is particularly good at absorbing UVB radiation, wavelengths from about 280 to 315 nanometers, which is the type of UV that causes sunburns and skin cancer and cataracts in humans. When an ozone molecule absorbs a UVB photon, it gains energy and breaks apart into an oxygen molecule, O2, and a free oxygen atom. That free oxygen atom can then combine with another O2 to form O3 again, or it can collide with another O3 molecule and form two O2 molecules, removing ozone from the system. It's a complex dance of creation and destruction, driven by sunlight and atmospheric chemistry that maintains a layer of ozone molecules in the stratosphere. This layer absorbs most of the sun's UVB and virtually all of the UVC before it can reach Earth's surface. And this absorption is critical, absolutely critical. Life on Earth evolved under this UV protection. Our cells, our DNA, are vulnerable to UV damage. UV radiation can break apart DNA molecules, causing mutations that lead to cancer and other problems. It can damage proteins, the molecular machines that make our cells function. It can kill cells outright if the exposure is intense enough. The ozone layer is why life was able to move from the oceans onto land roughly 400 million years ago. Before that, the land surface was essentially sterilized by UV radiation. Nothing could survive on land except maybe some hardy bacteria hiding under rocks or in the soil. The oceans provided protection because water absorbs UV. Even a few meters of water is enough to block most harmful UV. But as plants began producing oxygen through photosynthesis, atmospheric oxygen levels rose. And as oxygen levels rose, an ozone layer formed in the stratosphere. This ozone layer began absorbing UV, making the land surface safer. Plants could grow on land. Insects could evolve. Amphibians could crawl out of the water. Reptiles, mammals, eventually humans, all depend on the ozone layer for protection from UV. Now here's the problem. The ozone layer is created and maintained by a delicate photochemical balance, and that balance depends on more than just sunlight and oxygen. It also depends on Earth's magnetic field protecting the upper atmosphere from high-energy particles from space. Under normal conditions with the magnetic field intact, most high-energy particles from the sun and from cosmic sources are deflected away or absorbed by the magnetosphere before they reach the atmosphere. The particles that do make it through, mostly near the poles, interact with the upper atmosphere in the thermosphere and mesosphere, above the stratosphere where the ozone layer is located. But without the magnetic field, high-energy protons from the solar wind and cosmic rays from deep space would penetrate much deeper into the atmosphere than ever before. They'd reach the stratosphere, and when they collide with molecules there, they cause chemical reactions that destroy ozone. Specifically, high-energy particles colliding with nitrogen molecules N2, which make up most of the atmosphere, can break them apart and create nitrogen oxides, molecules like NO and NO2 collectively written as NOx. These nitrogen oxides are catalytic ozone destroyers. That means a single nitrogen oxide molecule can destroy many ozone molecules before the nitrogen oxide itself is removed from the atmosphere. Here's how it works. A nitrogen oxide molecule, let's say NO, collides with an ozone molecule O3. They react. The NO takes one oxygen atom from the O3, forming nitrogen dioxide NO2 and leaving behind an oxygen molecule O2. So one ozone molecule is destroyed. But then the NO2 can collide with a free oxygen atom O and react to form NO again plus O2. The NO is regenerated and can go destroy another ozone molecule. This cycle can repeat many times. One NO molecule might destroy hundreds or thousands of ozone molecules before it's eventually removed through some other chemical reaction or rains out of the stratosphere. This catalytic destruction is why certain chemicals are so dangerous to the ozone layer. Chlorofluorocarbons, CFCs, were widely used in the 20th century as refrigerants and aerosol propellants. They're very stable at Earth's surface, which is why they seemed like good industrial chemicals. But when they drift up into the stratosphere, UV light breaks them apart, releasing chlorine atoms. And chlorine is an even more effective catalytic ozone destroyer than nitrogen oxides. One chlorine atom can destroy tens of thousands of ozone molecules before it's removed. This is why the discovery of the ozone hole over Antarctica in the 1980s caused such alarm. Scientists realized that CFCs were being broken down in the stratosphere, releasing chlorine, and that chlorine was destroying ozone much faster than it could be created. A hole in the ozone layer was opening up over Antarctica every spring, a region where ozone levels dropped by 50% or more. The response was the Montreal Protocol, signed in 1987, one of the most successful international environmental agreements in history. Nations around the world agreed to phase out CFCs and other ozone-depleting substances. Production stopped. Atmospheric concentrations began to decline. The ozone hole began to recover. By the 2050s or 2060s, scientists predict the ozone layer should return to pre-1980s levels. But all of that assumes Earth's magnetic field remains intact. Now imagine what would happen if the magnetic field disappeared. High-energy particles, protons from the solar wind, and cosmic rays from space would penetrate deep into the stratosphere. They'd collide with nitrogen molecules and oxygen molecules, creating nitrogen oxides and other reactive species. The rate of ozone destruction would increase dramatically. At the same time, ozone creation would continue at roughly the same rate because it depends on UV light from the sun breaking apart oxygen molecules, and the amount of UV reaching the stratosphere from the sun doesn't change just because Earth's magnetic field is gone. But if destruction increases while creation stays the same, ozone concentration drops. The equilibrium shifts. The ozone layer thins. Research published by the European Space Agency, based on computer models of what happens during geomagnetic reversals when Earth's magnetic field weakens to 10 to 25% of normal strength, suggests that even a temporary weakening could reduce ozone concentration by 20 to 40% in some regions, particularly over the poles where the magnetic field lines normally funnel particles and where, without the field, particles would still tend to concentrate because of atmospheric circulation patterns. A complete loss of the magnetic field, not just a weakening but a total collapse to zero, would likely be far more severe. The bombardment of the stratosphere by high-energy particles would be unrelenting day and night everywhere on Earth. Atmospheric chemistry models developed by NASA and by independent research institutions suggest that ozone depletion could reach 30 to 50% globally within the first few days after the magnetic field collapsed. Over the polar regions where particle influx is highest and where the stratosphere is thinnest, losses could be 60 to 70% or even higher. Let's be conservative and say that within the first 24 hours after the magnetic field disappears, ozone depletion reaches 30% globally averaged, with severe losses up to 60% over the Arctic and Antarctic. What does that mean for life on Earth's surface? What does it mean for us? It means more ultraviolet radiation reaches the ground, a lot more. Specifically UVB and some UVC radiation wavelengths between 100 and 315 nanometers that are normally almost completely blocked by the ozone layer and by molecular oxygen in the stratosphere. UVB radiation wavelengths from 280 to 315 nanometers is what causes sunburns. It damages the DNA in skin cells. With repeated exposure, it causes skin cancer, melanoma being the most deadly form. It causes cataracts in the eyes, clouding the lens and leading to blindness if untreated. It suppresses the immune system, making people more vulnerable to infections. UVC radiation, even shorter wavelengths from 100 to 280 nanometers, is even more dangerous. It's capable of directly shattering DNA molecules, breaking the chemical bonds that hold the double helix together. It kills cells outright. It's so effective at destroying biological molecules that hospitals and laboratories use UVC lamps to sterilize equipment and surfaces. A few seconds of UVC exposure can kill bacteria, viruses, mold spores, anything biological. Under normal conditions, virtually all UVC is absorbed by ozone and oxygen high in the stratosphere. It never reaches the surface. Most UVB is also absorbed, with only a small fraction making it through. But with 30% ozone depletion, and with high-energy particles continuously creating nitrogen oxides that attack ozone, UV levels at Earth's surface would begin climbing sharply within hours of the magnetic field collapse. The UV index, a standardized international measurement of ultraviolet radiation levels at the surface, developed by the World Health Organization and used by meteorological agencies worldwide, normally ranges from 0 to 11 plus in most inhabited areas. A UV index of 0 to 2 is considered low risk. You can stay outside safely for hours with minimal sun protection. A UV index of 3 to 5 is moderate. You should use sunscreen if you're going to be outside for more than an hour. 6 to 7 is high. Sunscreen is recommended, and fair-skinned people can burn in 15 to 20 minutes. 8 to 10 is very high. Protection is necessary. Burns can occur in 10 to 15 minutes. 11 plus is extreme. Burns can occur in less than 10 minutes, and outdoor activities should be limited during peak sun hours. On a typical summer day in mid-latitude cities, New York, Rome, Tokyo, the UV index might reach 7 or 8 at noon, perhaps 9 on a very clear day. In tropical regions or at high altitudes, the Andes, the Himalayas, the East African highlands, the UV index can reach 10 or 11, but those are under normal conditions with a full ozone layer. With significant ozone depletion, 30 to 50% globally, the UV index values could spike to 15, 20, 25 or even higher in some regions. These are levels that have never been recorded in human history outside of the most extreme conditions at very high altitudes near the equator. At a UV index of 20, Exposed skin would burn in less than 5 minutes. Fair-skinned individuals, those of Northern European descent with light complexions, might burn in 2 to 3 minutes. Even darker-skinned individuals who have more melanin providing some natural UV protection would burn in 10 to 15 minutes. Blistering, painful second-degree sunburns that normally take an hour or more of beach exposure in midsummer would occur in the time it takes to walk from your car to a building, from your house to the mailbox at the curb, from the school bus to the school entrance. Eyes would be damaged by brief direct exposure to sunlight, not just discomfort or squinting from brightness, but actual tissue damage. Photokeratitis, essentially a sunburn of the cornea, the clear front surface of the eye, would become common. Symptoms include pain, redness, tearing, swelling of the eyelids, a feeling of sand or grit in the eyes, sensitivity to light and temporary vision loss. It's the same injury that occurs from welding without proper eye protection, or from snow blindness, when sunlight reflects intensely off snow and ice. And this wouldn't just be a problem in the tropics where the sun is high in the sky and UV is normally most intense. It wouldn't just be a problem at high altitudes where the atmosphere is thinner. It would be global, universal, north and south, equator to poles, sea level to mountains. During the day, when the sun is up, UV radiation would be dangerous everywhere. People would notice quickly. Within the first day, news reports would start appearing. Unusual sunburn reports flooding hospitals and clinics. Dermatologists overwhelmed with patients showing severe burns from what should have been brief outdoor exposure. Someone who walked their dog for 10 minutes. A parent who took their child to the park for 15 minutes. A construction worker who was outside for half an hour and is now in the emergency room with second-degree burns covering their arms and face. Social media would light up with photos and complaints. People comparing burns, asking if anyone else is experiencing this, sharing pictures of reddened skin, of blisters forming. The hashtag would trend. Sunburn epidemic, extreme UV. What's happening to the sun? Scientists would quickly realize the connection. The magnetic field collapse has led to ozone depletion, which has led to extreme surface UV. Warnings would go out. Emergency broadcasts on television and radio for those still working without power. Messages on social media on whatever internet infrastructure is still functioning. Government alerts sent to phones. Stay indoors during daylight hours. If you must go outside, cover all exposed skin, long sleeves, long pants, gloves, wide-brimmed hat, UV blocking sunglasses rated for 100% UVA and UVB protection. Apply SPF 50+ sunscreen to any skin that might be exposed. Seek shade whenever possible. Sales of sun protection products would explode. Stores would run out of sunscreen within hours. Online retailers would be overwhelmed with orders, assuming the internet and delivery systems are still functioning. UV protective clothing, the kind with tight weaves and special fabrics designed to block UV, would become impossible to find. Wide-brimmed hats, UV-blocking sunglasses, anything that could shield skin and eyes from the suddenly hostile sunlight would become precious commodities worth their weight in gold. But humans are intelligent and adaptable. We could adjust our behavior. We could stay indoors during the day. We could cover up when we have to go outside. We could shift our schedules, becoming more nocturnal, doing outdoor work and activities at dawn, dusk, and nighttime when the sun is low or below the horizon and UV levels drop dramatically. It would be disruptive. It would change how society functions. Cities that are vibrant during the day with people walking, shopping, eating at outdoor cafes would become deserted. Streets would be empty from sunrise to sunset. activity would shift to the hours after dark, but we could survive it. We have the technology and the intelligence to adapt. The real catastrophe wouldn't be what happens to humans. We'd manage, at least in wealthy countries with resources. The real catastrophe would be what happens to the rest of the biosphere, to the plants and animals and ecosystems that have no way to protect themselves, no way to understand what's happening, no ability to change their behavior or use technology to shield themselves from UV. Plants can't buy sunscreen. Animals can't check the UV index and decide to stay inside. Marine organisms can't understand that the light from above has become deadly. And that's where the true catastrophe begins. Let's start with the oceans, because that's where the foundation of Earth's food web lives. Phytoplankton. The word comes from Greek, phyto meaning plant and plankton meaning wanderer or drifter. These are microscopic organisms, most of them single-celled algae and cyanobacteria, that drift in the upper layers of the ocean, the top 200 meters or so where sunlight penetrates. They're so small that a single drop of seawater might contain thousands or even millions of individual cells. And yet, despite their tiny size, phytoplankton are arguably the most important organisms on Earth. They perform photosynthesis, using sunlight, carbon dioxide, and water to produce sugar and oxygen, just like trees and grass and crops on land. But because the oceans cover 71% of Earth's surface, and because phytoplankton are spread throughout those oceans wherever there's enough light and nutrients, their total biomass and productivity are enormous. Phytoplankton produce roughly 50% of Earth's oxygen. Think about that. 1 of every 2 breaths you take, the oxygen came from phytoplankton, not from forests or grasslands. Tiny microscopic organisms floating in the ocean, invisible to the naked eye, are responsible for half the oxygen in the atmosphere. They're also the foundation of the marine food web. Zooplankton. Tiny animals eat phytoplankton. Small fish eat zooplankton. Larger fish eat small fish. Whales, seabirds, seals, dolphins, all the charismatic megafauna of the ocean depend either directly or indirectly on phytoplankton. Remove the phytoplankton and the entire structure collapses. Now here's the problem. Phytoplankton are extremely sensitive to ultraviolet radiation. These organisms evolved to live near the ocean surface where there's plenty of sunlight for photosynthesis. But throughout their entire evolutionary history, they've been protected from UV by the ozone layer. They've never had to deal with high UVB levels, let alone UV. Their cells are vulnerable. They don't have thick cell walls or protective pigments or DNA repair mechanisms sufficient to handle intense UV exposure. When UV radiation hits a phytoplankton cell, several things happen, all of them bad. First, UV damages their photosynthetic machinery. Photosynthesis takes place in structures called chloroplasts, which contain chlorophyll and other pigments that capture light energy. UV radiation, especially UV, damages these pigments and the proteins involved in photosynthesis. The efficiency of photosynthesis drops. The cell produces less sugar, less energy. Growth slows. Second, UV damages DNA. Just like in human cells, UV can cause breaks in the DNA strands, mutations in the genetic code, errors that prevent the cell from functioning properly or from reproducing successfully. Third, UV causes oxidative stress. It generates reactive oxygen species, highly reactive molecules that damage cell membranes, proteins, and other cellular structures. It's like rusting from the inside. The cell's machinery breaks down. Studies conducted by marine biologists over the past few decades, experiments where phytoplankton cultures are exposed to elevated UV levels in the laboratory, where natural populations are observed during times when the ozone layer is thinner, like during the Antarctic ozone hole, have shown that even moderate increases in UVB radiation can significantly reduce phytoplankton productivity. A study published in the journal Nature found that a 20% increase in UVB exposure, roughly what you'd get from a 20% reduction in ozone, decreased phytoplankton growth rates by 10 to 15% on average. Some species are more sensitive, some less, but the overall trend is clear. More UV equals less phytoplankton. Now imagine not a 20% increase in UV, but a 50% increase, or a 100% increase, or even more in regions where ozone depletion is most severe. Phytoplankton populations in the upper ocean, particularly in tropical and subtropical regions where sunlight is most intense and where the sun is high in the sky for much of the year, would begin to decline within days of the magnetic field collapse and the resulting ozone depletion. Their photosynthetic machinery would be damaged faster than they could repair it. Their DNA would accumulate mutations faster than cellular repair mechanisms could fix them. Their reproduction rates would plummet. Many cells would simply die, killed outright by UV exposure. Within weeks, satellite observations of ocean color, which scientists use to estimate phytoplankton density by measuring the green chlorophyll pigment they contain, would show alarming declines. Satellites like NASA's MODIS, Moderate Resolution Imaging Spectroradiometer, and the European Space Agency's Sentinel satellites continuously monitor ocean color from space. The images they produce show vibrant blue-green colors in productive ocean regions, where phytoplankton are abundant, darker blue in less productive regions. Scientists studying these images in the weeks after the magnetic field collapsed would see the blue-green colors fading, darkening, turning to deep blue. The vibrant productive regions of the ocean, the equatorial upwelling zones, the coastal waters, the high-latitude blooms, would be dimming as phytoplankton populations crashed. A 20 to 30% decline in phytoplankton populations globally within the first month would be a realistic and even conservative estimate under severe UV stress. You might think, okay, 20 to 30% is bad, but 70 to 80% of phytoplankton would still be there, right? The ocean would still be producing oxygen, fish would still have food, things would be degraded but not catastrophic. But that's not how ecosystems work. That's not how food webs respond to losing their foundation. In ecology, there's a concept called the trophic pyramid. It describes how energy and biomass are distributed across different levels of a food web. At the bottom, you have primary producers, organisms that make their own food through photosynthesis. On land, that's plants. In the ocean, that's phytoplankton. The next level up, you have primary consumers, herbivores that eat the producers. In the ocean, that's zooplankton, tiny animals that graze on phytoplankton. Then you have secondary consumers, carnivores that eat the herbivores, small fish that eat zooplankton. Then tertiary consumers, larger fish that eat small fish, and so on up to the top predators, sharks, tuna, whales, seabirds. At each level of this pyramid, energy is lost, a lot of energy. The rule of thumb in ecology is that only about 10% of the energy at one level makes it to the next level. The other 90% is lost as heat, used for metabolism, excreted as waste. This means that if you have 1,000 kilograms of phytoplankton, they can support about 100 kilograms of zooplankton, which can support about 10 kilograms of small fish, which can support about 1 kilogram of large fish. It's a pyramid, wide at the base, narrow at the top. Now what happens if you reduce the base of the pyramid by 20 to 30%? You don't get a proportional 20 to 30% reduction at higher levels. You get a much larger reduction because the pyramid amplifies losses. If phytoplankton biomass drops by 30%, zooplankton populations might drop by 50% or more because they're not just losing food, they're also facing increased mortality from starvation, disease, predation. Small fish populations might drop by 70%, large fish by 90%. The numbers get worse the higher up the food chain you go. Commercial fisheries, which provide protein for billions of people and represent a multi-hundred-billion-dollar global industry, would face catastrophic collapses. Fish stocks that were already under pressure from overfishing, climate change, and pollution would plummet. Fishermen in Southeast Asia, West Africa, the Pacific Islands, regions where fish are the primary source of protein and where fishing is the main livelihood for millions of people, would pull up empty nets. Day after day, week after week, the catch would dwindle. First, the big fish would disappear, then the medium fish. Eventually, even the small fish would be scarce. Fishing communities would face economic devastation and food insecurity. People who have depended on the ocean for food for generations, for thousands of years, would suddenly find that resource gone. And it's not just commercial species, it's the entire ecosystem. Whales, which depend on huge quantities of small fish and krill, would struggle to find enough food. Mothers wouldn't be able to produce enough milk for their calves. Calves would starve. Populations would crash. Dolphins and seals, also high on the food chain, would face the same fate. Seabird colonies, places like the Galapagos Islands, the Falklands, the coasts of Peru and Chile, where millions of birds nest and raise chicks, would see mass die-offs. Adult birds, unable to find enough fish to feed themselves and their chicks, would abandon nests. Chicks would starve by the hundreds of thousands. The colonies, which have existed for millennia, would fall silent. And critically, the oxygen production from phytoplankton would decline. Remember, phytoplankton produce about 50% of Earth's oxygen through photosynthesis. If their populations drop by 20 to 30%, that's a 10 to 15% reduction in global oxygen production. Now, before you panic, let me reassure you, this wouldn't cause us to run out of breathable air in the short term, not in weeks or months or even years. Earth's atmosphere contains about 21% oxygen by volume. The total amount of oxygen in the atmosphere is enormous, about 1.2 times 10 to the 18th kilograms. That's an almost incomprehensible amount of oxygen. And oxygen doesn't just disappear if it's not being produced. It's chemically stable in the atmosphere. The only way oxygen is removed is through processes that consume it, like respiration by animals and plants, decomposition of organic matter, combustion, oxidation of rocks and minerals. These processes do consume oxygen, but slowly. If all oxygen production stopped entirely right now, it would still take thousands of years for atmospheric oxygen levels to drop significantly enough to affect human health. So a 10 to 15% reduction in oxygen production, while concerning, wouldn't cause immediate breathing problems, but the trend would be clear and deeply worrying. Earth's oxygen production capacity would be diminishing. The balance between oxygen production and consumption would be shifting, and if phytoplankton populations didn't recover, if UV levels remained high indefinitely, then over decades and centuries, atmospheric oxygen levels would slowly begin to decline. Future generations, centuries from now, might live in a world where oxygen levels are noticeably lower, where breathing feels harder, where physical exertion is more difficult, where high altitudes become uninhabitable because there simply isn't enough oxygen in the thinner air. But that's a long-term concern. In the immediate term, within the first weeks and months after the magnetic field collapsed, the bigger problem would be ecosystem collapse and food security. On land, the situation would be equally dire, perhaps even more immediately visible. Crops, the plants we depend on for food, wheat, rice, corn, soybeans, barley, vegetables, fruits. These species were domesticated thousands of years ago from wild ancestors. They've been bred and selected for high yields, good taste, ease of harvesting, resistance to pests and diseases. But they were never bred to handle extreme UV exposure because it was never necessary. The ozone layer has always been there, protecting them. They simply don't have the traits needed to survive in a high UV environment. Many crops are sensitive to UV damage. Their leaves, which are optimized for capturing visible light for photosynthesis, don't have sufficient protective mechanisms against intense UVB and UVC radiation. When UV hits a plant leaf, several things happen. First, UV damages chlorophyll, the green pigment that captures light energy for photosynthesis. Damaged chlorophyll is less efficient, and photosynthesis slows down. The plant produces less sugar, less energy for growth. Second, UV damages the photosystem proteins, the molecular machines that perform the actual chemistry of photosynthesis. These are complex, delicate structures, and UV can break them down faster than the plant can repair or replace them. Third, UV damages DNA in plant cells just like in animal cells. Mutations accumulate, cells malfunction or die. Fourth, UV causes oxidative stress, generating reactive molecules that damage cell membranes and other structures. The result, plants exposed to high UV grow more slowly, they produce fewer leaves, they flower later or not at all, they produce fewer seeds, yields drop. A comprehensive study published in 2019 in the journal Nature Communications examined the effects of elevated UVB radiation on various crop species. The researchers found that even moderate increases in UV, the kind that might occur during a geomagnetic reversal when the magnetic field weakens but doesn't disappear entirely, can reduce crop yields by 5 to 20% depending on the species and the intensity of UV exposure. Wheat is moderately sensitive. Rice is quite sensitive. Soybeans are very sensitive. Corn is somewhat tolerant but still shows reduced yields under high UV, with severe ozone depletion 50% or more, and the resulting extreme UV levels at the surface. We wouldn't be looking at 5 to 20% yield reductions. We'd be looking at 30 to 50% yield reductions for many staple crops, possibly even higher for the most sensitive species. Some crops might fail entirely in regions with particularly high UV exposure, tropical and subtropical areas where the sun is high in the sky year-round. Agricultural catastrophe would unfold within a single growing season. Farmers planting wheat in the spring would watch their crops struggle. The seedlings would emerge, but they'd grow slowly. The leaves would show signs of damage, brown spots, necrotic patches where cells had been killed by UV. By midsummer it would be clear the crop was failing. Yields at harvest would be a fraction of normal. What would normally produce 4 tons per hectare might yield 2 tons or less. Rice paddies in Asia, which feed billions of people, would show similar problems. The rice plants would be stunted, yellowed, producing fewer grains per plant. Soybean fields in the Americas, critical for both animal feed and human consumption, for oil and protein, would be devastated. Soybeans are particularly sensitive to UV, and the plants would simply not thrive under the new conditions. Food production would decline sharply across the globe, just as humanity would need every resource to adapt to the crisis. Food prices would skyrocket as supply dropped and demand remained constant or even increased due to panic buying and hoarding. Countries dependent on food imports would face shortages. Bread, rice, cooking oil, all the staples that people rely on would become expensive or unavailable. Famines would threaten regions that were already facing food insecurity before the crisis. Parts of sub-Saharan Africa, South Asia, Central America, the Middle East, places where malnutrition is already a problem, would face catastrophic hunger. Wealthy nations would hoard grain reserves, wheat stored in silos for emergencies, and would restrict exports to ensure their own populations were fed. The global food trade system, which currently moves millions of tons of grain, meat, produce, and other foods across borders every day, would fragment. Countries would prioritize feeding themselves over trading with others. International cooperation would be strained to the breaking point. The ideals of global solidarity would be tested against the reality of national survival. And it wouldn't just be annual crops. Forests and other ecosystems would suffer too. Trees, especially in tropical and temperate regions, would begin showing signs of UV stress within weeks. The leaves, evolved to capture sunlight for photosynthesis, would be damaged by the intense UV. You'd see discoloration, brown spots appearing on leaves where UV had killed cells. The trees would look sick, unhealthy. Over time, growth would slow. Trees wouldn't add as much wood each year. The growth rings, the annual rings you can see when you cut down a tree, would be narrower, showing that the tree was stressed, not growing well. Forests would become more vulnerable to disease and insect pests. A healthy tree can fight off infections and infestations. A stressed tree, weakened by UV damage, can't. Bark beetles, fungal infections, all the threats that forests normally handle would become overwhelming. Some tree species would die outright, unable to adapt to the new UV levels. Others would struggle on, diminished, weakened. Over the course of decades, entire forest ecosystems would shift. UV-sensitive species would decline or disappear. More UV-tolerant species would gradually replace them, but this transition wouldn't be smooth or quick. It would involve vast areas of dying forest, increased wildfire risk as dead vegetation accumulated, loss of habitat for countless species, and a massive disruption of the carbon cycle as forests transitioned from carbon sinks that absorb CO2 to carbon sources that release it as dead trees decompose or burn. Biodiversity would plummet. Species that couldn't adapt quickly enough to the new UV environment would face extinction. Amphibians, frogs and salamanders and newts would be hit particularly hard. They have sensitive, permeable skin that absorbs water and oxygen, but also allows UV to penetrate. Many amphibian species are already in decline worldwide due to habitat loss, pollution, climate change, and a deadly fungal disease called chytridomycosis. Adding intense UV stress would push many species over the edge into extinction. Insects, which play crucial roles in pollination, decomposition, and food webs, would also suffer. Studies suggest that UV radiation damages insect vision, navigation, and reproduction. Bee populations, already declining due to pesticides, habitat loss, and disease, would face another major stressor. Pollination services, critical for many crops and wild plants, would decline. Birds and mammals protected somewhat by fur or feathers would still suffer because their food sources would be declining. Insectivorous birds would find fewer insects. Herbivores would find less nutritious, UV-damaged plants. Carnivores would find fewer prey animals as populations at lower trophic levels crashed. The cascading effects would ripple through every ecosystem on the planet, from the tiniest plankton to the largest whales, from soil bacteria to forest canopies, from coral reefs, which would be bleaching and dying not just from warmer ocean temperatures but also from increased UV stress, to polar ice sheets, which would be melting not just from climate change but also from reduced reflectivity as UV-absorbing algae grew on the surface. Ecosystem collapse, biodiversity loss, food web disruption, all happening simultaneously, all reinforcing each other, all accelerating the transformation of Earth from a vibrant, living planet to something colder, simpler, harsher. And all of this, the UV catastrophe, the atmospheric erosion, the ecosystem collapse, the agricultural failure, would be happening at the same time as technological infrastructure was failing due to solar storms and radiation. Because while we've been talking about the slow long-term consequences of losing the magnetic field, there are also immediate catastrophic consequences for technology. And those consequences would begin within the first day or two, 24 to 30 hours after the magnetic field collapsed. Day 1, moving into Day 2. By now, scientists around the world would have confirmed the unthinkable. The magnetic field is gone. Government briefings would be underway in capital cities. Emergency response plans would be drafted. The public would be starting to understand the severity of the crisis as news spreads. But while humanity struggled to process this catastrophe, while officials tried to coordinate responses, while ordinary people wondered what it all meant for their lives, the cosmos would continue its relentless, indifferent motion. The sun doesn't care that Earth's magnetic field has vanished. It continues its normal cycle of activity, following the 11-year solar cycle and the shorter-term fluctuations driven by magnetic activity in its interior and atmosphere. And purely by chance, by the kind of random bad luck that makes catastrophes even worse, let's say a coronal mass ejection, a CME, that erupted from the sun a day or two ago is heading directly toward Earth right now. This isn't far-fetched. It's actually quite likely. Coronal mass ejections happen regularly. During solar maximum, the peak of the 11-year cycle, large CMEs occur several times per week. Even during solar minimum, they happen every few days. And they're not all directed at Earth. Most fly off in other directions. But the ones that do head our way typically arrive within 20 to 40 hours after launch, depending on their speed. So it's entirely plausible that a CME was already in flight when Earth's magnetic field collapsed, and now it's going to arrive and hit a planet with no protection. Let's imagine this is a moderate CME, not the largest on record but certainly significant. It carries about 10 billion tons of plasma, ionized hydrogen and helium, traveling at 800 kilometers per second. That's fast, about 1.8 million miles per hour, fast enough to cross the Sun-Earth distance of 150 million kilometers in about 52 hours, a little over 2 days. The CME launched from the Sun on what we'll call Day -1, the day before the magnetic field collapsed. It's been traveling through space while Earth's crisis unfolded, and now on Day 1, approximately 30 hours after the field collapsed, the CME arrives. Under normal circumstances, when Earth's magnetic field is functioning, a CME of this size would cause a strong geomagnetic storm, The solar wind plasma embedded with magnetic field lines would slam into Earth's magnetosphere, compressing it on the day side. The interplanetary magnetic field carried by the CME would interact with Earth's field. If the IMF is oriented southward, opposite to Earth's field, magnetic reconnection would occur at the magnetopause, allowing energy and particles to flood into the magnetosphere. Auroras would intensify, visible at much lower latitudes than normal, maybe as far south as the northern United States or Central Europe. GPS signals would degrade due to ionospheric disturbances. Some satellites might experience glitches, Wandersendemeterau. Power grids at high latitudes, in places like Quebec or Scandinavia, might experience induced currents that could, in a worst case, cause local blackouts or damage transformers. But generally, with the magnetic field intact, we'd weather the storm. It would be a notable event. Scientists would study it, but it wouldn't be catastrophic. Now remove the magnetic field. The CME's plasma, 10 billion tons of ionized gas moving at 800 kilometers per second, slams directly into Earth's upper atmosphere with nothing to slow it down, nothing to deflect it. The consequences would be immediate and catastrophic across multiple fronts. First, satellites. There are currently thousands of active satellites orbiting Earth. In low Earth orbit, LEO, at altitudes of 200 to 2,000 kilometers, there are satellites used for Earth observation, weather monitoring, some communications, scientific research, and the International Space Station. In medium Earth orbit, MEO, around 20,000 kilometers, there are GPS satellites and some communications satellites. In geostationary orbit, GEO, at 35,786 kilometers, there are communications satellites, weather satellites, and others. All of these satellites are designed to operate in the space environment, which is harsh. There's radiation, high-energy particles, extreme temperature swings, vacuum. Satellites are built with radiation-hardened electronics, shielding, redundant systems, and other protections, but they're designed assuming Earth's magnetic field is there, providing a baseline level of protection. The magnetosphere blocks most of the solar wind. It deflects cosmic rays. It contains regions of trapped radiation, the Van Allen belts. But satellites are designed to either avoid those regions or to handle the radiation levels there. Without the magnetic field, all those assumptions are invalid. When the CME hits, satellites would be exposed to radiation levels hundreds or even thousands of times higher than normal. The plasma contains high-energy protons and electrons that would bombard satellite electronics. Solar panels which convert sunlight to electricity using semiconductor materials would be damaged. High-energy particles striking the solar cells would cause defects in the semiconductor crystal structure, reducing efficiency. Over time, hours to days of intense bombardment, power output would drop. Satellites would have less electricity to operate systems. Computer systems, the brains of satellites that control everything from attitude to communications to data processing, would experience single-event upsets. ESUs, where a single high-energy particle strikes a transistor or memory cell and flips a bit, changing a 0 to a 1 or vice versa. Under normal conditions, satellites experience occasional CUs, maybe a few per day, and they're designed with error correction to handle it. But during a CME, without magnetic protection, CU rates would skyrocket, hundreds or thousands per second. Error correction systems would be overwhelmed. Computers would crash. Software would become corrupted. Systems would fail. Some satellites would go into safe mode, an automatic protective state where non-essential systems shut down to preserve the spacecraft. Others would lose attitude control, unable to point their antennas at Earth, or their solar panels at the sun tumbling helplessly. Some would fail completely, electronics fried, no longer responding to commands from ground control. Within hours of the CME's arrival, satellite operators around the world would be watching in horror as their spacecraft went dark, one by one. Communications satellites that provide television, internet, telephone services to remote areas, ships at sea, aircraft would stop functioning. The signals would cut out, TVs would show no signal, internet connections would drop, phone calls would fail. GPS satellites, the constellation of 31 satellites that provide positioning, navigation, and timing services used by everything from smartphones to aircraft to power grids, would begin to fail or provide degraded, inaccurate signals. GPS requires extremely precise timing, and if satellites' atomic clocks are disrupted by radiation, or if the satellites lose attitude control and can't maintain proper orientation, the system degrades rapidly. Without GPS, navigation becomes difficult or impossible for anyone relying on it. Ships at sea, already struggling because their magnetic compasses are useless, would now lose GPS too. Aircraft which use GPS for navigation and precision approaches to airports would have to rely on older, less precise navigation systems. Cars with GPS navigation would show incorrect positions or no position at all. And it's not just navigation. GPS timing signals are used to synchronize systems across vast distances. Power grids use GPS timing to coordinate the flow of electricity across the network. Financial markets use GPS to timestamp transactions with microsecond precision. Telecommunications networks use GPS to synchronize cell towers. If GPS timing fails, all these systems can experience problems. Weather satellites that monitor storms, track hurricanes, provide forecasting data would be lost. Meteorologists would go blind, unable to see what weather systems are developing, unable to warn people about approaching storms. Earth observation satellites that monitor crops, forests, ice sheets, ocean health, all the data that scientists use to study our changing planet would be crippled or lost. The International Space Station, orbiting at about 420 kilometers altitude, would be in grave immediate danger. Astronauts aboard the ISS, currently there are usually 6 to 7 crew members from various nations, would face lethal radiation exposure within hours of the CME's arrival. Under normal conditions, the ISS orbits within the magnetosphere's protection. Radiation levels are higher than on Earth's surface, about 50 to 100 times higher, because the atmosphere is thinner at that altitude. Astronauts receive about 150 to 200 millisieverts of radiation during a 6-month mission, equivalent to getting several hundred chest X-rays. That's considered acceptable, well below the dose that would cause acute radiation sickness. But during a solar storm without magnetic protection, radiation levels at ISS altitude would spike dramatically. Estimates suggest doses could reach 1 to 5 grays, maybe even higher over the course of a few hours. 1 gray is a serious dose. It's enough to cause acute radiation sickness, nausea, vomiting, fatigue, temporary drops in blood cell counts. 2 to 4 grays, severe radiation sickness, high risk of infection and bleeding, possible death within weeks without intensive medical treatment. 5 to 6 grays, survival is unlikely even with medical care. Above 10 grays, death is essentially certain within days. Mission Control in Houston would recognize the danger immediately. Radiation alarms on the ISS would be sounding. Dosimeters carried by astronauts would show rapidly climbing numbers. the order would come: evacuate immediately if possible. If a Soyuz or Crew Dragon spacecraft is docked, which there usually is for emergency returns, the crew would have to make a rapid decision: undock now and return to Earth, a process that normally takes hours of preparation, but that could be rushed in an emergency. The descent through the atmosphere would take only a few hours, and once below about 80 kilometers altitude, in the thicker atmosphere, radiation levels would drop to safer levels. But if no return vehicle is ready, or if for some reason they can't evacuate, the astronauts would have no choice but to shelter in the most protected areas of the station. Probably the Russian service module, which has more mass and shielding than other sections. They'd gather their sleeping bags, water containers, food, anything with mass that can provide additional shielding and create a makeshift bunker. They'd monitor their radiation doses and wait. Hours would pass. The dosimeters would climb. 1 gray, 2 grays, 3 grays. They'd know with sick certainty that they're accumulating doses that will have long-term health consequences: increased cancer risk, possible organ damage, potential infertility. Some might reach doses high enough to cause acute radiation sickness. They'd start feeling nauseous. They might vomit. Fatigue would set in. If doses exceeded 4 or 5 grays, some crew members might not survive even after returning to Earth. It would be a nightmare scenario, and it would be happening 400 kilometers above a planet that could do nothing to help. But the damage wouldn't be confined to space. It would reach all the way to the surface. High-altitude aircraft, commercial airliners flying at cruising altitude of 10 to 12 kilometers, 30 to 40,000 feet, would experience dangerously high radiation levels. Under normal conditions, cosmic radiation at cruising altitude is about 50 to 100 times higher than at sea level because there's less atmosphere above to shield from radiation. Pilots and flight attendants who spend thousands of hours per year at altitude receive annual radiation doses of about 2 to 5 millisieverts, considered an occupational hazard, but within safe limits. During a solar storm without magnetic protection, radiation at cruising altitude could spike to 100 times normal or more. A transatlantic flight, normally about 7 hours, might expose passengers and crew to radiation doses equivalent to dozens or hundreds of chest X-rays, maybe even reaching doses measured in grays rather than millisieverts. Airlines would have no choice but to ground all flights worldwide until the solar storm passed. Hundreds of thousands of flights canceled, millions of passengers stranded. Global air travel, already disrupted by the loss of GPS and the need to avoid polar routes due to UV, would come to a near-complete halt. But the most devastating impact would be on the power grid. On Earth's surface, the magnetic field collapse and the arrival of a CME would induce massive electric currents in the ground and in long conductors like power transmission lines. These are called geomagnetically induced currents, GICs. They're produced when the magnetic field changes rapidly, inducing electric fields in the Earth's crust through Faraday's law of electromagnetic induction. Under normal conditions, during a geomagnetic storm with the magnetic field intact, the magnetosphere compresses and wobbles, causing the magnetic field at the surface to fluctuate. These fluctuations induce GICs that flow through the ground and find their way into power lines, pipelines, communication cables. Power transformers are particularly vulnerable. Transformers are designed to handle alternating current, AC, at specific frequencies, 50 or 60 Hz depending on the country. But GICs introduce quasi-direct current, DC, into the system. Transformers aren't designed for DC. When DC flows through a transformer, it causes the magnetic core inside to become saturated. The transformer overheats. the copper windings get hot, insulation begins to break down. In severe cases, the transformer can be permanently damaged or destroyed. The famous Quebec blackout of March 1989 was caused by GICs during a relatively moderate geomagnetic storm. The storm triggered by a CME induced currents that overloaded transformers in Quebec's power grid. The entire grid collapsed in less than 90 seconds. 6 million people lost electricity for up to 9 hours. Some transformers were damaged and required weeks to repair or replace. That happened with Earth's magnetic field providing significant protection and reducing the severity of GICs. Now imagine the same scenario but with no magnetic field at all. The CME would interact directly with Earth's ionosphere and surface. The magnetic field changes would be orders of magnitude stronger than anything ever recorded during a geomagnetic storm. The induced currents would be catastrophic. Transformers across entire continents would be hit simultaneously. North America, from Canada through the United States to Mexico, Europe, from Scandinavia to the Mediterranean, Asia, from Russia through China and India to Japan, South America, Africa, Australia. Every grid on the planet would be under assault. The induced currents would massively exceed anything the transformers were designed for. They'd overheat within minutes. Safety systems, circuit breakers designed to trip and protect equipment would activate, but the scale and simultaneity of the event would overwhelm protective measures. Power grids would cascade into failure, starting from the high-voltage transmission lines that carry electricity across long distances, hundreds of kilometers. Failures would propagate. A transformer in one substation overloads and trips offline. The load redistributes to other transformers, overloading them. They trip offline. The cascade spreads like dominoes falling. Within hours of the CME's arrival, perhaps even faster, billions of people could lose electricity. Cities would go dark. Not just lights, but everything. No heating or air conditioning, no elevators, no traffic lights, no water pumps to deliver water to upper floors of buildings, no sewage pumps, no refrigeration for food and medicine. Hospitals would switch to backup generators, but fuel supplies would be limited, enough for maybe a few days at most. Operating rooms in the middle of surgeries would face terrifying decisions as power flickered and died. Intensive care units with patients on ventilators, on life support machines, would have only hours before backup power ran out. And this wouldn't be a temporary outage. Replacing damaged transformers is a slow process. Large high-voltage transformers, the kind used in transmission networks, are not mass-produced commodity items you can order online and have delivered next week. Each one is custom-built for a specific location and voltage level. They're manufactured in specialized facilities, often overseas, and they take 12 to 18 months from order to delivery under normal conditions. Each one costs millions of dollars and weighs hundreds of tons. They're not kept in large stockpiles because they're so expensive and because each grid only needs a certain number. If you have spares, you might have a few, maybe enough to replace 1 or 2 failures, but not dozens or hundreds. A simultaneous, widespread transformer failure across North America or Europe or Asia, affecting hundreds or thousands of transformers, would be impossible to repair quickly. We're talking about years to fully restore the grid, not weeks, not months, years. Dr. Daniel Baker, director of the Laboratory for Atmospheric and Space Physics at the University of Colorado and one of the world's leading experts on space weather and its effects on technology, has testified before the United States Congress and written extensively about this scenario. In his words, a severe geomagnetic storm, even with Earth's magnetic field intact, could cause trillions of dollars in damage and take 4 to 10 years to fully recover from. Without the magnetic field, the damage would be catastrophic and recovery might be impossible without international cooperation on an unprecedented scale. Think about what that means. Years without reliable electricity, no power grid, no refrigeration, no modern communication, no internet, no cell phones, no computers, no supply chains delivering food and goods. Society as we know it would collapse. Within days, food supplies in stores would be gone. Without refrigeration, meat, dairy, fresh produce would spoil. What remains would be shelf-stable foods, canned goods, dried foods, and those would be bought up quickly as people panicked and hoarded. Without trucks delivering supplies because fuel pumps require electricity and because logistics systems require communication networks, stores wouldn't be restocked. Water treatment plants, which use electricity to pump and purify water, would fail. Cities would lose running water within hours as elevated storage tanks emptied and couldn't be refilled. Sewage treatment would stop, waste would back up, public health crises would loom. People would be forced to find water from rivers, lakes, wells, anywhere, and to boil it if they could to avoid disease. But boiling requires fuel, wood or gas, and in cities those resources are scarce. Disease would spread. Without sewage treatment, without clean water, diseases like cholera, typhoid, dysentery would become threats for the first time in developed nations in over a century. Law and order would fray. Police and emergency services, without communication and without the ability to respond quickly because vehicles couldn't refuel, would lose effectiveness. Looting would begin. Violence would increase as people fought over scarce resources. Governments would declare martial law. Militaries would be deployed. But maintaining order across entire nations without electricity, without communication, would be nearly impossible. The social fabric would tear. Communities that pulled together, that cooperated and shared resources would have a chance. Those that descended into every person for themselves chaos would suffer horrifically. Economically, the world would be in a depression that would make the Great Depression of the 1930s look mild. Global GDP would collapse, maybe 50%, maybe more. Most economic activity requires electricity, manufacturing, services, trade. All of it depends on power. Stock markets, already suspended during the initial crisis, might not reopen for months or years. When they did, valuations would be a tiny fraction of their former levels. Most companies would be bankrupt. Pension funds, retirement accounts, savings, much of the world's accumulated wealth would simply evaporate. International cooperation would be essential but strained. Wealthy nations would have resources to begin recovery, to manufacture replacement transformers, to rebuild their grids, to maintain some semblance of order. Poorer nations would be desperate. They'd lack the industrial capacity, the financial resources, the technical expertise to rebuild on their own. They'd need aid. But would it come? In a world where every nation is struggling, where resources are scarce, the instinct would be to help yourself first and others maybe later if you can. Geopolitical tensions would spike, competition for resources, accusations and blame, old rivalries resurfacing, the risk of conflict, Even war would be very real. This is the world humanity would face within days to weeks of the magnetic field collapsing and a major solar storm hitting. A world without power, without functioning technology, without global communication or trade. A world fragmenting back into isolated regions, each struggling to survive. And all of this, every bit of it, the UV catastrophe, the ecosystem collapse, the agricultural failure, the atmospheric erosion, the technological apocalypse would be happening simultaneously, layer upon layer of crisis compounding and reinforcing each other, pushing Earth and human civilization toward a tipping point from which recovery might not be possible. So after everything we've discussed, after imagining Earth without its magnetic shield, after exploring the cascading catastrophes that would follow, what can we say? First, should we be worried? Should this keep you up at night? The honest answer is not immediately, but we should be paying attention. Earth's magnetic field is not going to disappear overnight. The geodynamo has been running for billions of years and will continue for billions more. Even if we're entering a geomagnetic reversal, which is possible given the field's current weakening and the fact that we're statistically overdue, reversals take thousands of years to complete. We have time, but that doesn't mean we should be complacent. The magnetic field is weakening. The North Pole is moving faster than ever before. The South Atlantic anomaly is growing. These are measurable changes happening right now, and we know from geological history that reversals do happen. The last one was 780,000 years ago. The average interval is 200,000 to 300,000 years. Statistically, we're overdue. And unlike many other existential risks, asteroid impacts, supervolcano eruptions, pandemics, this one is almost entirely out of our control. We can't prevent a geomagnetic reversal. We can't restart the geodynamo if it weakens. We can only monitor, prepare, and adapt. The good news is we're already doing that. Scientists are monitoring the field constantly. Space agencies are studying solar weather and developing better forecasting capabilities. Engineers are working on ways to protect power grids and satellites from geomagnetic storms. International cooperation on space weather is improving. If a reversal does begin in the near future, we'll have warning, we'll see the signs, and we can take steps to mitigate the worst effects. We can harden our infrastructure. We can develop backup systems. We can build redundancy into critical systems. We can even explore ambitious solutions like artificial magnetic shields, technological replacements for the natural field. The technology to do this exists, at least in theory. It would be expensive. It would require global cooperation, but it's not impossible. Humanity has faced existential challenges before and survived. Ice ages, volcanic eruptions, droughts, floods, plagues, wars. We're nothing if not adaptable. But adaptation requires knowledge. It requires understanding the threats we face. And that's why explorations like this one matter. Most people go their entire lives without thinking about the magnetic field. It's invisible, it's easy to ignore, but it's absolutely critical to our survival. Without it, Earth would be Mars, cold, dry, airless, dead. With it we have oceans, atmosphere, forests, life, civilization. So the next time you see the northern lights, those shimmering curtains of green and red, remember what they represent. Not just beauty, but protection. A visible reminder of the invisible shield that's been guarding us for billions of years. And remember that this shield, this magnetic field humming quietly in the background, is still working perfectly right now. It's been running for 4.5 billion years, and with any luck, it will run for billions more. We're safe, for now, and as long as we stay vigilant, as long as we continue studying and monitoring and preparing, we'll be ready for whatever the future brings. Thank you for joining me on this journey into one of science's most frightening scenarios. If this has given you a new appreciation for the invisible forces protecting us, if you're looking at the sky a little differently now, then please hit that like button, subscribe to the channel, and leave a comment. Tell me where you are in the world. What time is it there? What are you thinking about after this exploration? I read every comment, and I love hearing from you. The magnetic field is still there, still strong, still protecting everything we love. Sleep well tonight, knowing the shield is holding, and I'll see you in the next video.